In this third video for homework packet 4.3, we're going to take a look at graphing again, as we have in the previous homework packets and this homework packet, but we're going to take a look at graphing, in this case, rational equations. Now we'll remember from previous lessons that a rational equation is an equation where you have one polynomial over another polynomial. In other words, a big giant fraction. Okay? So I've got x squared plus 2x minus 8 all over x squared plus 7x plus 12. Now the question is, what does the general shape of a rational equation look like? That's a really tough question to answer because it could take on so many different shapes. However, there are some defining features of rational equations that we can discuss that gets us down the road really well for what the equation is going to look like. And then what's going to happen is we're going to use our calculator's graphing abilities in order to finish off what the graph looks like. So here's what we always want to do when we are graphing a rational equation. We want to write our equation in three different forms. The first form is the form it's given to us in right here, standard form. The second form that we want to write it in is in factored form. So I'm going to look at the top and bottom and factor as much as I can. I see that they're both quadratics, so I'm potentially going to be able to factor into the two separate binomials. If I look at x squared plus 2x minus 8, I need two numbers that multiply to negative 8 and add to 2. And I know it's an x and an x right here because of the x squared. I think to satisfy the multiply to negative 8 and add to 2, it's going to be a plus 4 and a minus 2. 4 times negative 2 is negative 8. 4 plus negative 2 is the positive 2. I do that now the same thing with the denominator here. And I need two numbers, well, I've got x and x because of the x squared, and then I need two numbers that multiply to 12 and add to 7. I believe that's going to be a 4 and a 3, x plus 4 and x plus 3. 4 plus 3 is 7, 4 times 3 gives me my 12. So I'm now in factored form. The third version, if possible, that I want to write my equation in is in simplified factored form. What I mean by that is, are there any factors both top and bottom here that cancel each other out? And hopefully we see that the x plus 4s are going to cancel out. So what I can do is I can write this as x minus 2 all over x plus 3 because the x plus 4s would have canceled out. So we have three forms: standard form, factored form, and simplified factored form. Each one of these forms is going to communicate something very important to us. The first and last form are what we're going to start with. I'm actually going to start with this last form. This last form right here is going to tell us what is called a vertical asymptote. A vertical asymptote. So a vertical asymptote, if you remember from exponentials where there was a horizontal asymptote, a horizontal dashed line, right? In this case, we are going to have a vertical dashed line, and that occurs whenever the denominator is equal to 0. Well, in our case, our denominator equals 0 when x is negative 3, because negative 3 plus 3 would be 0. So our denominator is 0 when x is negative 3. Therefore, on my graph at negative 3, I have what's called a vertical asymptote. Okay? I am going to draw it with a dashed line. Good. So that's the vertical asymptote. And what's interesting is a rational equation doesn't just have a vertical asymptote, it also has a horizontal asymptote. And we get the horizontal asymptote when we, excuse me, when we look at the original form, standard form, what we do when we are asked to find the horizontal asymptote is we look at the first two terms of the equation, x squared over x squared, and then I reduce it. What is x squared over x squared? It's same thing over the same thing. That reduces to 1. So y equals 1 is where my horizontal asymptote is. So at y equals 1, I am going to draw a dashed horizontal line. So in these equations, we have both vertical asymptotes and horizontal asymptotes. And keep in mind, if nothing had canceled out right here, I would have had two values that would have made my denominator 0, which means I would have had two vertical asymptotes. We'll see that potentially in the homework packet. Okay, so here's the point at which I now need to ask myself the question in regards to x and y intercepts. Okay, interestingly enough, these lines are how my graph is going to be confined. Horizontal and vertical asymptotes essentially behave in a way that break my equation up into separate parts. We're going to let the calculator show us what those parts look like. However, I can still find my x and y intercepts. Okay, to find my x-intercept, I plug 0 in for y. Now, it makes it really easy to use the fully simplified form to find your x and y intercepts. So to find your x-intercept, you plug 0 in for y. That's 0 equals x minus 2 all over x plus 3. Now, here's a quick trick. If a fraction is supposed to equal 0, what's the only piece of the fraction that has to be 0? The numerator. It doesn't matter what the denominator is. It could be 5 million, but as long as the numerator is 0, then the fraction equals 0. So the question is, what value of x makes the numerator equal to 0? And we can see from the x minus 2 that an x equals 2 would make the numerator 0, thus the whole fraction 0, because 2 minus 2 is 0. So x equals 2, I'm going to put a dot right there, is where my x-intercept is. Now my y-intercept. To find my y-intercept, I plug 0 in for x. So y is equal to 0 minus 2 all over 0 plus 3. It's fairly easy. Again, I use the simplified factored form to do this. And I find that that simply equals y equals negative 2/3. So I'm going to go down to y equals negative 2/3 on my graph and put a dot. Okay, so I know that that's where my graph crosses the x and the y-axis. But I also know that the vertical asymptotes I drew confine my graph. I can't cross over those points. Now, we're going to learn, I'm going to show you in class and then a separate video how to graph something on your calculator. But if I were to take and graph this on my calculator, here's what it'd end up looking like. And there we go. Okay, it would end up looking like that. Notice that the vertical and horizontal asymptotes cut the graph up into pieces so that they don't cross over the asymptotes at all. And notice that to the left and to the right, it follows this horizontal asymptote that we had constructed. And then vertically speaking, this vertical asymptote cuts our graph in half. Okay, so important things to notice in the process of graphing a rational equation. And again, remember, not knowing exactly how these two portions look like is okay, because we're going to use our calculator to be able to know those pieces. But the pieces we can find before we use our calculator to help us graph are the pieces, our x-intercept, our y-intercept, and our horizontal and our vertical asymptotes. So because rational equations are so involved, we need to do another example together, because there is another potential intricacy involved here that we want to take special care to worry about. So again, let's go through the same process. We want to make sure that we are putting it in the three forms that we need it to be put in. So I first want to put this in factored form. To do that, what I'm going to notice is my numerator isn't factorable into the two binomials right away. What I do notice is that every term has a 3 in it. So I'm going to quickly rewrite this as 3 times x squared plus 5x plus 6. I factored a 3 out of each piece. Okay? So now I'm going to put this in factored form. Y is equal to what? 3 times what times what on the numerator? I already factored the 3 out, but what now can I factor the x squared plus 5x plus 6 into? What two numbers multiply to 6 and add to 5? I believe it's going to be an x plus 2 and an x plus 3. 2 times 3 is 6, 2 plus 3 is 5. I think we're golden. Now, let's look at the denominator. X squared tells me I have an x and an x. Now, let's ask the question, what values of x, multiply to 4 and add to 5? I believe the only combination is a positive 1 and a positive 4. 1 times 4 is 4. 1 plus 4 is 5. Now, here's the interesting piece about this example. Can we write a simplified factored form? Is there anything here that cancels out? And the answer is no. There's nothing here that cancels out. So there's no simplified factored form that we need to take a look at. But what we can do is we can start looking at vertical and horizontal asymptotes. Factored form, again, is where we look at vertical asymptotes. And we always look at where the denominator equals 0. So what are the values of x where my denominator equals 0? Well, if I look at that, it looks like at x equals -1 and x equals -4. Those would be the two values of x that make the denominator equal to 0. So at -1, I'm going to put a vertical asymptote, and at -4, I'm going to put a vertical asymptote. So interestingly enough, in this one, we have two separate vertical asymptotes. Okay. Now, let's talk about horizontal asymptote. If we recall, for horizontal asymptote, we look at the first terms, top and bottom, 3x squared over x squared. And I ask myself, can I simplify that? And I can. The x squareds cancel out, and I'm simply left with 3. So y equals 3 would be my horizontal asymptote. So I'm going to make a horizontal line here at y equals 3. Now, a quick side note to mention is that in both the examples we've looked at, the top and bottom have been both x squared. What if the top and bottom had been something to the effect of maybe a 3x over x squared? Anytime the exponent in the denominator is bigger than the numerator, okay, the horizontal asymptote ends up occurring at y equals 0. So essentially the x-axis. Because what would this reduce to? 3 over x. Because x over x squared, one of the x's cancels out in the denominator, and this x cancels out up here. So 3 over x. Oh, how do you graph 3 over x? In the context of a horizontal asymptote, what this means is 0. The reason being is your horizontal asymptote goes really far left and right in the x direction. What happens to 3 over x when x gets really, really big, positive or negative? It would get really, really close to 0. So keep that in mind. Okay, so we've got all of our vertical and horizontal asymptotes. Let's talk x-intercepts and y-intercepts really quick. Okay, so x-intercept. Find your x-intercepts, you plug 0 in for y. So 0 equals 3 times x plus 2 times x plus 3 all over x plus 1 times x plus 4. Now, remember that in order for a fraction to equal 0, the only thing that has to be equal 0 is the numerator. So in factored form, that makes it really easy for us. Where does it say that our x-intercepts are? It says that our x-intercepts are at x equals -2 and x equals -3. Those are the two values from each of those factors that would make the numerator equal to 0. So my x-intercepts are at -2 and -3. Great. What about my y-intercept? To find my y-intercept, I plug 0 in for x. Now, what is y going to equal? If there is no simplified factored form, really easy way to do this is, if I go back up to this original equation and I plug 0 in here, 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 and here, all of these terms become 0, and what does y equal? 18/4, which reduces to 9/2, which as a decimal is 4.5. So I know my y-intercept up here is at 4.5. And there we go. Good. So the question now that we need to ask ourselves is, what does this look like when we graph it? Okay, so again, what we're going to do is in class we're going to look at how to use our graphing calculator, and then also I'll construct a separate video on it. When you use your graphing calculator, I'm plugging it in right now, the graph that you end up with ends up looking like this. This region over here has a curve that's bound and separated from everything else by the horizontal and vertical asymptote. The region in the middle comes up here through and down the x-intercepts here, and then the region over here almost looks like a reflection of this first piece, comes down through the y-intercept and then levels off at the x-intercept. Again, we're going to use our calculator to see those pieces, but the main thing is to be able to identify the vertical and the horizontal asymptotes.